Welcome to Learning Outcome 2, all about software, the programs and instructions that bring the hardware to life. We'll explore the three big families of software, system, application, and development, and see how each one plays its part. So, what exactly is software? It's the set of programs and instructions that tell the hardware what to do. Without it, even the most powerful laptop is just a lump of inert electronics. Software is what actually brings the machine to life. It's written by programmers in special languages and then run by the computer. And in this outcome, we'll describe the three main types: system, application, and development software. It helps to picture software as a stack of layers sitting between you and the hardware. Right at the top is the application software you work with directly, like your web browser. Beneath it sits the operating system, quietly managing the hardware. And below that is the firmware that starts the machine and gives low-level control. Each layer leans on the one directly beneath it, a bit like the floors of a building resting on the foundations. Software splits neatly into three broad families. System software runs and manages the computer itself. Application software helps you get a specific job done. And development software is what programmers use to create brand new programs. Every piece of software you'll ever touch falls into one of those three groups. We'll take each one in turn over the next few slides. Let's define the key pieces of system software. The operating system is the master program that manages the hardware, runs everything else, and gives you an interface to work with. Think Windows, Mac OS, or Linux. A device driver is the smaller piece of software that lets the operating system talk to a particular bit of hardware, such as your printer. And utility software covers the little maintenance tools like antivirus, backup, and disk cleanup that keep the whole system healthy. The operating system is the single most important piece of system software, so it's worth knowing what it actually does. It manages the processor, letting several programs run at once, a trick we call multitasking, and it manages memory, deciding what's kept in RAM. It also looks after your files through a system of folders and provides the interface while controlling input and output. Whether you're on Windows, Mac OS, or a Linux distribution like Ubuntu, it's the operating system juggling all of that in the background. Let's zoom in on device drivers. A driver is specialized software that acts as a translator between the operating system and a piece of hardware. And each type of device, whether a printer, a graphics card, or a webcam, needs its own. Modern systems come with loads of drivers built in and can install them automatically, which is what plug-and-play means when you plug in a new mouse, and it just works. When hardware misbehaves, an out-of-date or missing driver is very often the culprit. Utility software is all about keeping your computer healthy, secure, and running smoothly. This is the family that includes antivirus and anti-malware to fend off threats, backup software to guard against losing your files, and disk cleanup and defragmentation tools to keep storage tidy and quick. Compression tools that zip files down to save space belong here too. We count these as system software because they look after the computer itself, rather than doing a task for you like writing a letter would. Let's draw a clear line between system and application software. System software, the operating system, drivers and utilities, runs and manages the computer itself, usually quietly in the background, and the machine simply can't function without it. Application software, on the other hand, helps you carry out a specific task: a word processor, a browser, a game. You choose to open an application when you need it, and it runs on top of the operating system. One keeps the machine going, the other gets your work done. Application software is the stuff you actually open to get things done, and it comes in several categories. There's productivity or office software like word processors, spreadsheets, and presentation tools, web browsers such as Chrome, Edge, and Firefox, and media players for your music and video. Then there's creative software for editing images, video and audio, and of course games, from a quick phone puzzle to a demanding 3D title. Chances are you've used something from most of those categories just this week. Here's a quick tour of application software with real examples. For productivity, you've got the likes of Microsoft Word and Excel to create documents and crunch data. For browsing the web, there's Chrome, Firefox, and Edge. Media players such as VLC handle your audio and video. Creative tools like GIMP and DaVinci Resolve edit images and film, and communication apps like Microsoft Teams and Zoom keep meetings running. Each one is built for a particular kind of task. Now we come to development software, the tools programmers use to build new applications and even system software. Its job is to turn human-readable code into programs the computer can actually run, and to help teams manage their work along the way. The specification names three main kinds: the IDE, the compiler, and version control. Every app on your phone started life in tools like these. Let's define those three development tools. An IDE, or Integrated Development Environment, is an editor with built-in tools for writing, testing, and debugging code, Visual Studio Code, and PyCharm being popular examples. A compiler translates the source code a programmer writes into the machine code the CPU can run, and version control tracks every change to the code over time and lets a team work together safely, with Git, often used with GitHub, being the classic example. Let's follow a real example from code to finish program. A student writes a simple C++ program to add two numbers, typing the source code into an IDE like Visual Studio Code. A compiler then translates that human-readable code into machine code the CPU understands, and the operating system loads and runs the result. They save their work in Git so they can undo mistakes and track versions. In one small project, you can see development software and system software working hand in hand. Software also differs in how it's licensed and shared, and the big distinction is proprietary versus open source. Proprietary software is owned by a company, its source code is kept closed, and you pay for a license, Microsoft Windows being the obvious example. Open source software makes its source code freely available for anyone to view and change, like the Linux operating system or the Firefox browser. That choice affects cost, support, security, and how freely you can adapt the software. Let's weigh up the strengths of each. Open source software is usually free to obtain, its code can be inspected and adapted, and a large community often means fixes appear quickly. Proprietary software tends to be more polished, comes with formal support and clear accountability from the vendor, and usually offers wide compatibility and readily available training. Neither is simply better. The right choice depends on what an organization needs and how much it can spend. Let's make this concrete with a new cafe, setting up computers for admin, marketing, and stock control on a tight budget. For system software, they pick an operating system that runs happily on affordable hardware. For applications, they choose a free Office suite like LibreOffice for letters and spreadsheets, plus a browser for online banking, and for utilities, they add free antivirus and cloud backup to protect their records. They skip costly development software because they're not writing their own programs. Matching the software to real needs keeps the bills down while still covering every task. Let's revisit firmware, the low-level software stored on a chip that controls a specific device, such as the UEFI or BIOS, on your motherboard. When you switch the computer on, the firmware checks the hardware is all present and then loads the operating system from storage into RAM. Only once the operating system is up and running can you open any application software. So firmware sits right between the hardware and the system software in that layered stack we saw earlier. Let's see software and hardware team up. When you click an application, the operating system loads it from storage into RAM and schedules the CPU to run it. Drivers then let that software use the hardware, whether that's sending a document to the printer or pushing graphics to the screen, and the results appear on your output devices, all coordinated by the system software. Software and hardware are genuine partners. Neither is much use without the other, and the system software is the bridge that connects them. Let's bring Learning Outcome 2 together. Software is the set of programs that tells the hardware what to do, arranged in layers from firmware at the bottom up to applications at the top. System software, the operating system, drivers and utilities, runs and manages the computer itself. Application software, from office suites to games, helps you get tasks done. And development software, the IDE, compiler and version control, is used to build new programs. Software can be proprietary or open source, and whichever it is, it has to work with the hardware through the operating system and its drivers. That wraps up Learning Outcome 2, and you should now have a clear sense of the software layers that turn hardware into a useful computer. To take it further, the reading list offers well-regarded books on operating systems and software engineering, along with journals covering operating systems and development practice. You'll also find friendly online resources, including Microsoft Learn, the Linux documentation, and a free book on Git, plus case studies comparing operating systems and following a student team using version control. Do explore the ebooks and journals on Moodle, as they'll reinforce these ideas and support your assignment.